The sum we see here is the sum of the volumes of all contributions of rectangles of this nature, where we have a delta y and a delta x at some position yi star, xj star, some position represented by yi star and xj star. And the dimensions of the rectangle are a delta y by delta x by f of xi star, xj star, yi star volume. So this is just a sum. This is a sum over any specific strip, any strip between two y values. Okay, so we have a series of rectangles as we did on this picture. And let me move back just a little bit so we can still see that picture. Okay, so we have a sum of rectangles across here. This sum represents the sum corresponding to all these rectangles. In this case now it's not an area, it's a sum of volumes. But you have the sum of the volumes, you have the approximate volume under your f of xy curve above this strip. Okay, well, that's actually what you have in this expression where I factored out the y sub I. No, actually, no, never mind. What I said is true. Okay, this is the volume corresponding to this strip. I can factor out the delta y sub I since it's the same across the whole strip, and I can put this into this form. Now what can I do? Well, what I want to look at is just this sum here. So I just want to look at this part of the sum. Sum from j equals 1 to m of f of xi star yj star delta xj, and it's yi and xj. Okay, make sure that the letters are properly formed. Just looking at this, okay, this sum as the delta xj's approach 0, this approaches an integral, as you know from first year calculus. And it's the integral of f of x yi star dx. I haven't yet put the limit on the integral, but this approaches this integral. Now, I'm assuming you understand how a Riemann sum works, okay? So we're just invoking that. So what we do in the limit, of course, in the limit as your delta xj's approach 0, your x-coordinate becomes essentially continuous. So you just talk about f of x, and your delta xj's become dx's. So this really represents, well, this represents this sum, approaches this integral. I don't want to say too much more about that right now. If I get too technical, it's going to become a little more difficult. And I think you have an intuitive idea of that. We want to make it more rigorous, but right now let's leave it where it is. Now, as j goes from 1 to m, what happens to x? Well, your x values go from here to here. That's from 0 up to the square root of y sub I star. So that this inner sum becomes this integral. So your volume approximation becomes the sum from I, again hesitating on that index, I equals 1 to n of the integral of f of x y I star that's a comma there, dx from 0 to yi star, and then times delta y sub I. Now that has a meaning that I really want to try to indicate by a picture, and that picture is going to kind of mess up a little bit of this picture, but it's important enough. Okay, if I'm confining myself to one single y sub I star, as I am here, and I've written that I like a J, okay, then I'm confining the function to the part of the three-dimensional graph above this line here where y equals y sub I star. We know that if I confine myself to this line down here in the plane, in the xy plane, that I have a plane parallel to the xz plane that cuts the graph of my function. One of the points where it cuts the graph is here. The other points, well, we don't know what the function does, but let's just say, okay, the function does something like this. So now I've cut the graph of my function f of xy with an xz plane parallel to this one. And now I've got this graph. And it's this function, which is now f of x y sub I star, that I'm integrating here. Letting my delta xj's go to 0, I get the integral of this continuous function. So that's what this is. Now I multiply that by delta y sub I, and now this graph takes on a thickness equal to my y sub I. I'm hesitating to do this because eventually I'm going to mess it up and it's not going to be at all comprehensible, but I'm going to kind of take the risk. I'm going to say, okay, I've got a rectangle here where I have a delta y sub j, delta y sub I in this direction, and I've got a similar rectangle over here, wherever. And the function remains identical all the way across. So now what I've got looks like this. Now I've kind of obliterated my original picture, and I hope I don't need it again, but I probably will. Okay, so now I've got this thing. Okay, it's got an area of this face that's equal to the integral of f of x y sub I star. It's got a thickness delta y sub I. So what I have here is a volume of the ith strip. Yeah, strip isn't quite the right word, but I can't think of a better one. And I'm summing that over all strips from I equals 1 to n. Well, in the limit, what is this approach? This approach is an integral with respect to y. I let my delta y sub i's shrink down to 0. And, of course, I'm summing over y intervals. So I'm summing over my y limits. I'm summing from y equals 0 to 2 because I have strips extending from 0 up to wherever 2 is. And we can see that here as well. So I'm integrating from 0 to 2. I'm integrating these volumes with respect, well, I'm integrating these volumes. Okay, so I'm integrating the integral from 0 to y of f of x y dx dy. Now I was careless up here, so I want to correct that, and hopefully you've been bothered by that. This should be the square root of y sub I star, because x goes up to the square root of y, right? So now we have this integral. Integral of f of x y dx from 0 to square root of y, and then that integrated with respect to y from 0 to 2.